quantum information and quantum computing. And I don't see the title, but like today he'll be telling us about application of this formalism he developed in the last couple of years, this double bracket formalism for implementing imaginary time evolution on a quantum computer. So the screen is yours. Marek, welcome. Yeah.
Okay. Hi guys. Thanks to Michał for letting me show you some new results that we have. So the seminar actually emerged from me meeting Michał here in Singapore, and we were walking around and I couldn't stop talking about it. And now I want to write down the formulas that I was telling him all the time, drawing in the air all the time. Okay, I assume you can hear me well. Just interrupt me anytime. It's supposed to be just a fun discussion. And okay, so anyway, just last month, or yeah, just before Christmas, we finished writing up a paper, which has basically 3 components. The most important one is that we are looking at the imaginary time evolution. So if I have an initial state psi 0, then if I want to find the ground state of a Hamiltonian H, then I can look at something called the normalized imaginary time evolution and define such a state vector. So after I normalize for any real tau, this will be a well-defined state vector, even though we are starting from a non-unitary propagator acting on our input state. Okay, so this is what I define as imaginary time evolution. And since the 50s or so about, I think it was year 51, when Mann and Lowe, they looked at this from the perspective of path integrals, and they found, okay, if instead of doing real-time evolution on some input state, if we instead do analytic continuation and just consider real time instead of imaginary time, or they call it imaginary time here, where the argument is fully real, then this imaginary time evolution, as psi goes towards psi of tau equals infinity, will be giving us a ground state of the Hamiltonian. There's a couple of fine prints that we should keep in mind. If you want to do it in finite time up to some epsilon, then the Hamiltonian, the input problem, should have a well-defined gap. And the initial state here should have at least some finite overlap with the ground state. And if we have this, then the imaginary time evolution, as we go with tau to infinity, will give us the ground state. Okay, so this is a nice thing where if we are doing quantum computing and we want to design a quantum algorithms for ground states of Hamiltonians, then if we look at the Hamiltonian, we can ask, okay, what can we do? How can we synthesize different circuits? And then eventually we want to compile it into gates so that we can run. And so today we are talking about designing quantum algorithms for the problem of finding the ground state given an input Hamiltonian. And our approach will be through this imaginary time evolution. And once we say, okay, we take...
Just one technical question. Do you allow for degeneracy of a ground space, or?
Yeah, so technically, okay. So, okay, let's have a look at that. If I apply e2 minus tau h to some psi 0, and I will write my Hamiltonian, let's say lambda k, lambda k, lambda k. Those will be my eigenstates. Then if I decompose this state here, we will be applying e to tau lambda k psi 0 lambda k. And what you see is if you have the ground state, which is lambda 0, it can be degenerate. This will be suppressed the least. And once we start normalizing by the norm of e tau h psi 0, then the entire ground state sector will be stabilized. So we don't know which one we will find, but ITE will land somewhere in the ground state. So So what we will have is that psi of infinity will be something like the projector on the ground state on the psi 0, and then we normalize. But we don't know exactly on which kind of state we will normalize.
Sure.
Yeah.
Thanks.
But it should still work. And everything in imaginary time evolution comes from this idea that if I look at the action of this Hamiltonian exponential, then I start suppressing exponentially every state. And the slowest suppression is lambda 0. And then if I divide by this, then actually this factors out and we stabilize the ground state, we get what we wanted. Okay, so that's the imaginary time evolution. The problem with this is the question, how do you implement this operator in nature? And I can talk about this philosophically for 1 hour, but basically you cannot do it easily, because if you could, you would be solving hard optimization problems, because the Hamiltonian could be encoding some cost function for max cut or something like this. If you can quickly implement this operation with the normalization, then you have a polynomial algorithm for NP. We don't believe it's that easy. But what we study is also, after imaginary time evolution, we ask about the problem of quantum imaginary time evolution. So psi of tau for every tau is normalized. So there should exist some unitary q tau that rotates psi 0 into that state for me. And the quantum imaginary time evolution problem is a problem in synthesis, asking if I am targeting ITE, how do I go in a unitary way through a unitary q tau into that state? Okay, so just to discuss this a little bit, if I have psi tau and I want to find a unitary q tau that rotates my psi 0, what I could do is to say, okay, I define this to be the first vector of my basis, and I will just view this as a basis transformation. Okay, and then you would think, okay, that's great, but the problem is that it doesn't solve, because it's, let's call it the kind of formal solution. Those unitaries always exist. But if we look at imaginary time evolution, we are applying e to tau h to psi 0. Then we are normalizing this action of the non-unitary propagator. And if we look at the state psi of tau, then it smoothly depends on tau. There exists some derivative that I can compute, and I will write down this equation in the second for the derivative. So what we want is that q of tau also smoothly depends on the imaginary time tau, okay? And that defines the problem of the synthesis for us. We want to find a systematic way of finding those unitaries q of tau, such that for every tau we find them and they are related to each other. And once we have that, we can talk about compilation, which I will talk about towards the end of the talk. Okay, so if I have my definition of imaginary time evolution here, I can do very simple calculations, and what I will find is that if I take the derivative of the numerator here, I will find e to minus h and nothing changes, so I have my state. And then I have to also take the derivative of the numerator. And what turns out is that this takes care of the normalization in the infinitesimal way. And there's a beautiful equation that looks like a nonlinear Schrödinger equation, where the normalization is ensured by adding here the mean energy of the Hamiltonian as you are flowing forwards in the imaginary time. Okay, so this equation is from the 50s, and it appears already in the Gelman-Lowe paper. People have studied, so just to say, people tried to synthesize those q of tau unitaries variationally. There's different approaches. Either you go variationally through a parametrized circuit, or there are also Krylov and quantum Lanczos approaches. All of them are asking about measurements, and basically point to point, you are searching for the unitary. And now I will tell you how to do it systematically with analytical calculations. So this equation, if you want, I can derive for you this equation now, but basically we just need to take the derivative of the square root of the inner product and it's fine. So I will just repeat what we have. We want to ask, as I'm cooling towards the ground state with the imaginary time evolution, I'm asking how does my state change? And it changes by the application of the Hamiltonian. And in order for this to remain normalized, I need to add a component in superposition with this, where I'm adding here this amplitude given by the energy. And this thing here is actually important because it encodes the nonlinearity of the problem. So we have a nonlinear differential equation here. Okay, so the next thing is a hint that I got from David Gossett very early on when I started working on double bracket flows. And he told me about something that he discovered when he was working on a problem where he wanted to improve QAOA, optimized over product states, and gain some energy advantage over this. And he realized that, long story short, his insight can be rewritten in the following way, that the differential equation for ITE can be written like this. So I got very excited when I realized what he meant by this. And then he wrote me a very nice email that he's busy and I should follow on with the project. But this equation is really very crucial for us. And yeah, I want to credit David for sharing this insight. Let me tell you why it's important. If I take a commutator of A, B, where those two are Hermitian operators, if I want to take the Hermitian conjugate of this operator, then I will have B dagger A dagger minus A dagger B dagger. And if they are Hermitian, then I have B A minus AB, which means that I have minus the commutator AB. So a commutator of two Hermitian operators is anti-Hermitian. If I have E to ITH on some say 0, then this is a unitary action because E to IH is also anti-Hermitian. So if I define this to be W bracket and I define this to minus bracket, then E to exponential bracket is a unitary operator on the qubit Hilbert space, okay? So even though I don't have an I here, there's no I here, there's no I here, a Schrödinger equation would have some I somewhere hidden, okay? Even though I don't have this, what I can write is that if I want to have psi of tau plus some d tau, then what I can do is I can exponentiate with d tau this bracket here. So we have the projector C of tau, H C of tau on psi of tau. Okay? So what we have is that Q of tau will be some Trotter-Suzuki decomposition over different times. So we will have d tau. I will write just psi Tn, comma H, dot, 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 d tau, psi T0, let's say, comma H. And that is our unitary, okay? So this equation here that David observed that it's equivalent to this equation here. It's directly after we look at this as a generator and recognize that the anti-Hermitian operator generates unitaries, we get a form for a Trotter-Suzuki decomposition of a kite unitary. And in the limit of d tau towards 0, we will get a smooth family of unitaries. Okay, so that's a really cool thing.
Can I ask something, Marek? So
yes.
Just to put it in different words, so you get that this time evolution is actually equivalent to time-dependent sort of time-dependent like Schrödinger equation, but with the non-linearity coming from the fact that effective Hamiltonian depends on a pure state as well.
Yes. Yes.
Okay.
And that totally
then you can either trotterize or do something more fancy with it. Okay.
Yeah, exactly. So that's what we do with the paper. We just study how to put it on the quantum computer. It's not, the story is not done yet because we need to do a couple of tricks. But this just already highlights to you that in this sequence of trying to find ground states on quantum computers through this observation by David, we already get a cool step forward. I mean, this is already putting us in a good position. Let's have a look at how that works. So the commutator first thing will be psi of tau. Then I will have h, and I'm applying this to psi of tau. So this thing here is e of tau. And so this term here is giving me this term here. And then I'm subtracting h times the projector as I had it. So it's really a simple observation once you have written it down, but I wouldn't know to write it down, right? So this gives me the first term, okay? So the commutator kind of gives you the right terms. So once you expand the commutator and just apply the projector in this equation, you recover the previous. So through this, we get this equation. So it's exactly the implementation. So this is just a better form to represent imaginary time evolution if we are aiming for this quantum imaginary time evolution with Q of tau. Okay. If there are no questions on this, let me tell you a little bit more why this was exciting for me once I realized the meaning of it. Let's look at the density matrix psi of tau. And now if I look at my equation here, okay, let me zoom out a little bit so I have both. We want to rewrite this equation for the density matrix. So what we will get is d tau psi of tau will be, the bracket here is acting like a Hamiltonian, so this w with psi of tau. But w is also a bracket that depends on psi of tau. And what we get is something called the double bracket flow. And specifically this equation is called a double bracket flow. And specifically there are different double bracket flows. The particular one that we talk about today is due to Roger Brockett, who found it at the turn of 80s to 90s, I believe. And there's entire monographs on the geometry of those things. I will tell you a little bit about this just now. Okay, but in the context of Warsaw, Professor Głazek was actually working on similar equations, searching for continuous ways of doing renormalization. So you might know it through some lectures in the Polish context. Okay, but this one specifically is due to Brockett, and it gives us directly a lot of information. So what we have is that the ITE, so the ITE is a solution to Brockett's double bracket flow, okay? And what it means is that we directly get a lot of properties from the understanding of double bracket flows. So what Brockett was interested in is he was looking at the optimization over a unitary adjoint manifold, a cost function that we normally don't look at in physics. So that was his cost function f of tau. And what he found is that there is a way of doing the steepest descent algorithm for this least square optimization with a constraint that this state psi of tau is a unitary rotation. So we have Q of tau of the psi of 0 matrix here. Okay, so restricted over unitaries. So if I want to minimize over unitaries a cost function where I have psi of 0, then we can set up the steepest descent algorithm, and it will turn out that the Riemannian gradient, so psi of tau, comma h, is the steepest descent operator in a very specific sense. And today I will not be talking too much about manifolds, but basically there's a way of embedding the unitary manifold to act adjointly in this way. It remains a Riemannian manifold, and you can look at the Riemannian gradient, and if you compute it, it will be this bracket here. So then just the steepest descent evolution will give you that the psi of tau should satisfy the Brockett's double bracket flow. But because ITE is a solution to Brockett's double bracket flow, and Brockett's double bracket flow is a steepest descent flow, that means that ITE is kind of optimal in terms of locality. Okay? Because
sorry, Mike, can I just jump in? So, okay, when I'm trying to make sense of this cost function, like I would intuitively think that it's probably something that you are saying probably holds, but when you, how to put it, like when you normalize your Hamiltonian in some sense, I don't know that the ground space would have zero energy. Do you do something like this, or it doesn't really depend? Because like intuitively, this thing is sort of, yeah, I'm a bit confused about it, because the minimal, like if you exactly hit the ground, maybe I'm wrong here. Even I'm not sure. Maybe sorry. Maybe.
Okay, so there are many answers to this question. So there's a monograph, an entire monograph on double bracket flows by Helke and Moore. And they study this from the dynamical systems perspective with all the equilibrium points and so on. As with our physics application, we kind of know the equilibrium points and all the issues that can pop up. Basically, we can characterize when the imaginary time evolution here is going to the ground state. Okay, so if imaginary time evolution goes nicely to the ground state, then this is equivalent that the density matrix of that ITE is solving the double bracket flow. Okay, and the double bracket flow in itself has those geometrical interpretations where you kind of understand now ITE. Because it's a solution, double bracket flow is a steepest descent flow. So ITE is also in a very specific sense a steepest descent flow. Okay. And the most important thing is that if I view the Hilbert space as a manifold where I want to take a point which is my psi of tau, and now I want to rotate this state by a unitary such that I am taking a gradient of my f of tau, then in the tangent space here, so I have a tangent space here, the direction that I should be taking is this element of the tangent space of the manifold. Okay? Now, I didn't prepare a full discussion to show that this is a manifold and derive this, but I can recommend this, and this is basically a monograph that explains and has appendices about all the geometry and so on.
But the manifold is just projective space, right? Or not? Like
so I made a drawing for the state psi of tau because that's what we want to rotate in on a quantum computer. Brockett was considering optimizing over the manifold of unitaries, this least square functional here. Okay.
Right.
And it will turn out that the gradient of f of tau, or if you make the cost function dependent on the point of a unitary with some starting point, then the gradient will be exactly this.
Sure, thanks. Thanks.
Okay, so there's a couple of things that I want to tell you. Normally, if you take psi of tau, you will never subtract the Hamiltonian from the density matrix. I mean, we usually don't do this. But it's actually very intuitive what happens here. I can consider the scalar product definition of the of this norm, and what we will get is that we will get the norm of psi of tau squared plus the norm of the Hamiltonian squared plus minus 2 times the real part of trace psi of tau times the Hamiltonian. Okay, so if we look at this way, it means that we have constant minus 2 times, and I had 1/2. Sorry, I had 1/2 here, 1/2 there. So there's actually a 1 minus the energy over time that I was defining already before. Okay, so that's the next magical thing. Not only are we doing a steepest descent flow over the optimization over those unitaries here, additionally, the cost function such that we are taking the gradient. So what we get is d tau of psi of tau will be the gradient over our manifold of the cost function, which is e of tau. And this is what ITE is doing. Okay, so ITE was known since the 50s, but it's really fantastic that it has all those properties. And usually I didn't see it being mentioned. It's actually in some recent papers from quantum information for optimizing on parameterized manifolds. Actually, Lucas had derived this equation independently, that basically ITE is a gradient descent, but it is actually a gradient descent of this cost function. Okay. So you can view ITE not only as this path integral idea, but actually you could derive it geometrically by some Morse function, where the Morse function is actually E of tau, and your manifold is rotating by unitaries. So this is really cool. Now I was trying to understand why David's trick worked, and then I was looking at some more of the things. So actually what happens is that a bracket cost function for any double bracket flow will be minus the norm of the bracket. So if in our case, it will be psi of tau comma h. Okay, so we have an analytical way of computing the change of the cost function. The change of the cost function is the length of our direction in the steepest descent direction. Okay, but because this is pure, what happens is that if you compute this norm, and I will, unless you ask me, I will not compute it because it's just 2 lines. But what happens is that if we evaluate this, actually thermodynamics kicks in. And what we find is that you can express the energy dynamics during imaginary time evolution as the fluctuation here. Okay, so psi of tau. So if you do a little bit of a computation, you find that you recover the variance here. So the change in energy over time during ITE is driven exactly by the fluctuation along of the trajectory. So it's a beautiful relation. And actually, it is essentially a speed limit of some sort, because locally the change is the fastest possible in the normalization of choosing the Hilbert-Schmidt scalar product and 2 norms. So those define for you the distances on the tangent space. But once you have this, locally, your changes are as fast as possible, and the velocity is actually driven by fluctuation. So we call it a fluctuation-refrigeration relation. So we have sometimes fluctuation-dissipation relations for thermal states. ITE is applying a thermal state to a pure state and normalizing, and this one has a fluctuation. So this is a fluctuation, and this is the energy fluctuation, and this is the kind of cooling rate. So after we derive the differential equation, we also have a differential equation for the energy change, and we can see that imaginary time evolution will be lowering the energy unless we have zero fluctuation. So that's also one answer to Michał's question, whether we will be getting stuck. So you can have zero energy fluctuation only in one case, that you hit exactly with equality and eigenstate. Otherwise, we will be converging to the ground state. Okay. So so basically, okay, we have this, and this is one point that I wanted to make. Maybe there's some questions, because next I will come to telling you how to put this on a quantum computer. And this thing here will be important because the quantum algorithm will in every step actually fulfill this relation as well. Okay. Okay. So how do we put it on a quantum computer? We had the synthesis equation based on the double bracket flow, where I was saying I should be taking those unitaries. So what we will do is we will define a quantum recursion. We will start with psi k, and we will take the commutator of the density matrix of this vector with the Hamiltonian H, and we will choose some small step size s, and that will give me an updated state psi k plus 1. Okay? So you see that this corresponds to those unitaries, because in every step, I'm taking a proxy for an infinitesimal step in the direction of the commutator, which is the right one to implement the imaginary time evolution. Okay, so this is what we refer to as double bracket height. Okay, and it has a few properties. Okay, so actually, this is the double bracket iteration. And what we need to work on is how to use those commutators. Okay, so in this Hemke-Moore book, the results that are presented there, they actually show you directly that this converges to the ground state as well. If you have an epsilon, then there exists a S non-zero such that you get up to an epsilon the ground state. And the convergence is exponential because we are doing a gradient flow. But now, how do we put this on a quantum computer? And the key step.
Sorry, Marek, can I stop you here? So imagine you had you were just sort of trotterizing and forget about like the cost of implementing those operations really.
Yeah.
What would be what would be complexity measured in a number of steps that you need to have epsilon precision?
Yeah. So so I will tell you a few things in a moment. Long story short, we will not get a polynomial time quantum algorithm based on our analysis, but we are relatively close to having good results. What I need to do next is to say, okay, we have an iteration that looks very good because it gives me a unitary, but I don't know how to compile this yet.
Sure. But my question is much simpler. Let's say we do it on paper, okay, and we have some oracle that magically gives us the way to implement it. But in this, let's say in this problem, I want to get epsilon close to the ground state, right? And I have, let's say I have a promise on the gap, and you do this trotterization, like how many steps, how many like unitaries of this form you will have to implement. Assume you can do it sort of exactly.
So we can show results on the fidelity. So in the paper, we use here the notation of sigma, but you see that I'm taking the pure state of the vector that I'm coming with, and I have some S0. And then what we can show is that the fidelity overlap with the ground state of the iteration will be converging exponentially fast towards 1. So if you give me a threshold for the fidelity that you want, it will be, k will be somehow a logarithm of this epsilon, where the q is this thing here that depends on the initial overlap and depends on the gap of the Hamiltonian and the norm.
Okay, I see. So this, you technically need this thing that you subtract smaller than 1, right? For it to...
And indeed so this is a couple of pages to compute it because we need a multiplicative bound, but we can relate the fidelity from one step fk plus 1. We can relate multiplicatively with fk, and then we can get this kind of exponential contraction. So this is a good thing because it converges fast. But this gap from 1 is actually going down in the thermodynamic limit.
Just a quick question here. How do you pick this optimal S0 kind of iteration size?
So I have a comment in the end matters for this one. We pick it very suboptimally, and we are writing a paper where we can choose it a bit better. But in this case, everything is decided around those formulas here somewhere, where actually your infidelity, so epsilons are the infidelities, they depend on the thermodynamic properties of the state encountered in the previous step. And we take very bad lower bounds. So the mean energy you can lower bound as the infidelity times the gap, and the variance you can upper bound as the infidelity. You say that all the infidelity is in the highest excited state. And here you take the opposite thing, but they should be satisfied simultaneously. So our bound is actually quite weak here. So the key thing here is this bound. And this is how the ratio of the Hamiltonian norm, the highest eigenvalue, and the gap lambda 1, how they appear. And okay, once we have those quantities, it's more or less clear how to do Taylor expansions, and we take some bounds and we bring it home more or less. So, but those bounds are very loose. And this time here, if you run some numerics, I actually have it open. You can look it up on GitHub, my name DBKite. You never need to do such small step sizes. I didn't even evaluate it, but normally you would take much longer time steps. Okay, so our analytics suffers here just from trying to derive general bounds. But in practice, what you would do is you would evaluate the energy and fluctuation on a quantum computer. And then you parameterize this bound, and that gives you a way of parameterizing this as 0. So this is maybe the only time in this talk where I will be talking about more heuristic things, because in the paper we focus on the analytics. But inside of the proof, I mean, there's very clearly ways of optimizing things if you have more information about what you encounter. Okay. So this S0 is just, I like it because it gives us this multiplicative stuff, but unfortunately it's just a geometrical bound, let's say. It's a worst case bound. Okay, yeah, come back to this in a moment if it's still not clear. The last thing that I need to say before I finish is how do we put it on a quantum computer, and it gives us a very cool way of combining unitaries. So there is something called the group commutator, which is a way of getting Lie brackets with multiplicative group structures. And up to a small error, we can approximate the group commutator as a product of the unitaries generated by A and B. So we need to go forward, forward, backward, backward. And you see that in the linear order, this would be this would cancel out. So what we get is that if I have a time s on every unitary, then I will get a second order approximation to the commutator, and the error bound will be s to power 3. Okay, so this is something called the group commutator. And there are also better approximations, and there are actually papers improving the Solovay-Kitaev compilation through longer product formulas that give you maybe O to S to power N approximations, and then
Coincidentally, we have author of this paper with us, tutor here.
Yes. So I actually got an email from Greg Kuppenberg. I don't know if you know him. It's a mathematician.
Yeah, of course, yeah.
Yeah, so he actually told me about some group representation papers. I can forward to you the email. Might be interesting to talk about this.
Absolutely, yeah.
Yeah. Anyway, don't ask me about inverse free algorithms because we have inverses here and we need them
Yeah.
for. Okay, long story short, if I have a psi of tau and a Hamiltonian and I want S, then I can do e to square root s of psi of tau here. I will need to change the order, e to I s square root h, e to minus I square root s h, because we have an either say plus minus sign. And then I need it in this order. Okay, good. So we have this approximation here. And the next thing is that in our case, we are always applying this to a state psi of tau. So if I apply e to psi of tau, I will just get simply a phase times this vector, which means that I can drop this one, which brings us to the definition from the paper. I will show you where this is in the paper in a moment. But what we get is that we have the Hamiltonian, e psi s psi, no, here I do the notation omega k, e to minus I s h, and I apply it to omega k. Okay. So what happens is that this is the group commutator approximation to this is the group commutator approximation to the bracket. And what we show is that the energy Ek plus 1 is Ek minus S times the fluctuation in the state plus O of S squared. So this is the fluctuation-refrigeration relation. Okay, so that works. And for this one, we are showing that the fidelity converges exponentially with this Q factor. Okay. Good. So this is our algorithm. Now you can ask, how do you do this one on a quantum computer? There are two answers. If you view this as some parameterization here, there's a way of doing it by opening the system up, and it's called density matrix exponentiation. Okay, so that's one way of doing it. Another way of doing it is to say, I have a reference state and there are some unitaries that brought me to omega k from a reference state 0. In this case, e to time times omega k, I will actually write it like this explicitly, is e to it uk 00 uk dagger. And I can use unitarity to bring it into this form, 00 uk. And what I meant by 0 is that this is a tensor product of zeros. And the unitary e to it, it's actually a very fun calculation, is a multi-qubit controlled unitary. And it needs number CZ is something like O of number of qubits. Okay, so, and the number of T gates is the same. So this is a multi-qubit controlled rotation with IT 0 on one single qubit, controlled over all other qubits. And there's an efficient way of compiling it. Okay, so I'm going a little bit fast, but let me repeat. So we took the group commutator. And if we look at the group commutator, there's one unitary that we apply to the state, which gives us a phase. So we dropped one, and we were left with this omega here. So what we have is that the density matrix of the state plays the role of the Hamiltonian. So you can do it as the density matrix exponentiation, or you can say that you are fine doing this multi-qubit rotation, which is just a constant circuit that you have. And then we have the unitary rotations. So what we get is, okay. From this, what we get is that if I want to find the unitary of UK plus 1, I need to go with the Hamiltonian, do the evolution, do the reflection, undo the previous step, then undo the Hamiltonian evolution, and then do the previous step, right? So this one will give me UK times 0. This together will give me UK plus 1, UK plus 1, acting on 0. Okay, so this will be omega k plus 1. And this is omega k. And here we have EISH, E2IS omega k, E2 minus ISH acting on omega k. Okay, so this is a correct way. But now if you look at this, I just told you that if you use those unitaries, you get a guarantee that you will lower the energy. Sorry, I dropped the minus. You will remove this amount of energy from the previous state by running those unitaries. So now what you see is that if you have some u theta, you can do an evolution with the Hamiltonian. You can do this multi-qubit controlled unitary, u theta, one more time, u theta, e to Hamiltonian, and you get a new circuit. And this one is guaranteed to improve over those things from, for example, from a VQE or QAOA or some MPS encoding. Okay, so the meaning of this one, thanks to those analytics, is that whatever circuit you had, you just need to repeat it 3 times. You echo forward and backward with the Hamiltonian, and you have a kick operation, a little bit like in echo experiments in a single qubit, but this is many body echo. And you put it together, you get a better unitary that is guaranteed to have a lower energy. Okay. So for me personally, this is the most exciting thing, because if I told you you have the task of taking a unitary, let's say here, you have to take a unitary 3 times and tell me what to put in between such that I get a new unitary and I get a lowered energy. I mean, it's not so clear how to chop it up. And thanks to the analytics, we actually chop into pieces a smooth flow, and we get this kind of formula here. Well, maybe I show this in the paper, it will be nicer. So in the paper, that's this equation 13 here. So you could call this U0, and then you get a U prime, such that just 3 repetitions of your unitary give you a better circuit, which is guaranteed to improve by this amount of energy. And of course, this S needs to be optimized so that we can drop the bounds here. But in the paper, you see it's 27 pages. We discuss a lot how to treat this. Okay, so that's one thing that we arrive at. So to me, this one is key. I was talking a little bit, so I'm starting to summarize now already. I was talking about this problem of synthesis and compilation. And thanks to those analytic properties with double bracket flows, we get a way of putting circuits together without knowing what they are, echoing between them and getting a better circuit. So we are really synthesizing obliviously without knowing what you optimized. We can improve on that with the guarantee. And the reason why we can do this is that we have steepest descent flows. So one way of interpreting the operations that we do, let's see somewhere here. When I'm doing such an operation or an approximation of this one, what I'm asking the quantum computer to do is to coherently apply unitaries that coherently go in the gradient direction. And that's the way to go, because in principle, you could measure those things and multiply the commutator classically, get some new generator that you call W, and do Hamiltonian simulation into gates. But it's very sensitive, it's very noisy. People tried it, and basically the measurement sensitivity limits you here. And now if those methods you should do as a warm start, and then once the measurements limit you, you just tell the quantum computer to apply a variant of approximating this bracket coherently. And it will lower, with a guarantee, it will lower the energy. So that kind of summarizes it summarizes more or less this equation here, that this is our approach. Now, Michał was asking about the gate counts. If we look at this here, to get one circuit that is improved, I need to do 3 times 1 to 3 times the previous circuit. So what we get is we get a query complexity 3 to power k of U0. So even if you do 3 or 5 layers of a VQE, very quickly that depth will blow up because I will have n CZ gates per qubit of the U theta, and then it will be amplified by 3 to power k. That's the pain of the algorithms. But this is because we are working coherently, and we have also worked on using DME to, so we have a paper, let me show you. I think so we wrote a paper called Quantum Dynamic Programming, because what we are studying in let's say, in this paper is a quantum recursion where the state coming in tells us what unitary to apply. So we define this to be a quantum recursion. The simplest example of a quantum recursion is the Grover algorithm. And then you can see that we are doing reflection operators here. And the reflection operators are unitary operators that depend on the state. So basically the state information can come in and tell you what unitary to apply. And so this is a notion of quantum recursions. And if you have a classical recursion, you do dynamic programming. And then we discuss how to do quantum dynamic programming. The outcome is that we get new algorithms as well. We call it oblivious-Schmidt decomposition, but we cannot clone like we can do classically. So there are trade-offs. Basically, we can take an exponentially long circuit like you have for Grover, and we can change the depth from exponential to polynomial at the cost of doing exponential width. So we don't have a full solution to questions that arise from having quantum recursions here. Okay, so that is giving more or less a full answer to Michał's question about the complexities. So if
can I just ask, because I don't know what k you need to get epsilon precision really, because maybe it's not so bad, like as a function of epsilon, right?
Yeah, if you fix the norm to be constant, it's very fast, but unfortunately, so if you want an infidelity less than delta, then delta should be q to power k. You take the logarithm on both sides, then you get log of delta. Wait, I can write with this. Log of delta by log q is your k. Okay. But q has this norm here and it's very bad. Okay. So to converge, you really need to work on this gap here such that every step of fidelity. So maybe let me explain the formula. So what we have is that if you do those states, then the fidelity to the ground state of the state will be amplified by a factor larger than 1. So we multiplicatively crank it up, and then we can go to infidelities and get this one. Yeah. But the gap that we have here has this factor here. And that basically removes efficiency of the runtime. Because, okay, I should say for a local Hamiltonian, we will have theta of n. The norm will be growing very fast. I mean, linearly with the number of qubits. So basically, this is 1 over n to power 3. I think we can lower this at least to 2. Maybe it is possible to power 1. But probably you need to have this because probably you need to, in the hard case, have a small step size in the thermodynamic limit. Yeah. So it is possible that you need to have this lowering, but yeah. So the problem is that if we would if this wouldn't be here, we would be violating some complexity conjectures. No, I mean it would be going too fast because we have the complexity 3 to power k. If k is log of n, then we would start being quasi-polynomial or polynomial, and that's a bit of a problem, but it's not the case here.
Right. So Marek, like how much time do you need? Because we are sort of reaching close to one.
That's more or less the summary. So the key thing is this equation here, which translates to unitaries. So the results are more general, where you could take any Wormstadt unitary, repeat it 3 times. Together with those operations, you get a unitary that is better. We have those thermodynamic things in the background, so we can relate the energies through thermodynamic quantities. We have really nicely looking bounds on the fidelity, but it's too small to give us a polynomial time quantum algorithm. So that's the open question. Can you improve our analysis? So during the talk, I was pointing to the appendix where really the kind of loosening of the bounds is happening. And then there's like the more conceptual things that we have. So we showed that the imaginary time evolution has an analytical way of writing it as a double bracket flow. So a differential equation where the psi appears twice, so it's a nonlinear equation. But it facilitates for us the synthesis in terms of the commutators here. And from this, we built the algorithms by chopping this into products, and we approximate the brackets by products, and that gives us the final equation. Okay, so this is our standing point. We are working on applications to other tasks of the double bracket flow, so I'm happy to discuss this, but I think that's for now the contents of the paper.
Cool. Many thanks, Marek, for the great talk. Like maybe yeah, thanks. So let's move to discussion. Like if there are any questions or comments to Marek, Carol.
Yes, hello. Good afternoon or good evening in Singapore. So more general question, because I'm not so much familiar with this theme. So you mentioned double bracket flow, and is it reasonable to ask about some further generalizations like triple bracket or multiple brackets?
Yes.
In spirit of, let's say, Baker, Campbell, Hausdorff expansion, yes?
Okay, I have the book here. So that gives me also an occasion to say something good about the book, because I learned about it when I was finishing resubmission of the first paper. It's a book by Helmke.
Show me the book again.
Yeah.
Yes. Helmke. Okay.
So Helmke, I think, is still active, or I think is a professor in Munich.
Yeah, I met him once. Yeah.
So actually, that community, Brockett was one of the co-authors of the PRA that showed that you can do a 2-qubit unitary with 2 CZ gates. The time optimal paper, it's this Brockett, it's the middle author of that, and he is a professor, I think, at Harvard or Princeton for systems control, nonlinear control.
Yes.
And so they wrote this entire book, and somewhere here as an exercise, there's the exercise, if you take a doubly nested commutator, it will be actually the imaginary time evolution with h to power 2.
I see. Yeah, because I realized there was also a paper about triple commutators by Marek Czachol many years ago, but I think very different story. But well, so triple commutators, but they are different, I think. Okay, so this is one question, and the second one, the last. What happens if for H or Hamiltonian, you just take some basically random, like Gaussian orthogonal ensemble matrix? Isn't this an interesting question, or can you get some averages, how it looks like for generic behavior?
Okay. So our analysis depends on the gap of the Hamiltonian. So that's one important thing. And we are writing a paper actually where we have a different case where the gap is maybe given and the norm is also given. Let me show you, for example, the numerics. So what happens if you start with the numerics, you get one step gives you this huge decrease. So you want to go to -13. We are talking about 8 or 10 qubits, Heisenberg model. So we start from a product state -7 and we just halfway there after one step. Okay. But if we look at the nodes, let's say here, it's actually not that surprising because we are implementing the imaginary time evolution, and basically very quickly we got rid of the high energy noise. Okay, so very quickly you get an energy decrease, but it's a very cheap way of cooling, and the variational quantum eigensolver can do that as well. Where it gets stuck is when you go to the more complex cold states and you need to somehow select between those two. So with the GOE, it might be nice, but one problem that you have, there's actually a paper by Kothari and Childs where they give limitations on Hamiltonian simulation of dense Hamiltonians. If you give me something from GOE, well, I could try to maybe cook it up with some spectrum and some T-designs to say this is some diagonal thing and so on. But one question is, can you do the Hamiltonian simulation with those Hamiltonians? If you want to study the speed of convergence using GOE just to get some bounds on the speed, you can do this, but we have very good bounds for the imaginary time evolution. So if you have a gap, we can show that up to, if you want to go to epsilon, we need the imaginary time for gap systems needs to be logarithmic in n. So this is also in the appendix of our paper.
Sorry, Marek, can I just jump in because you mentioned Kothari Child's paper, but very about complexity of implementing GUE evolution, right? Or Hamiltonian simulation for that.
Yeah.
So just just wanted to complement that with Marcin Kotowski, we had a paper that gave lower bounds, like exponential lower bounds for complexity of implementing. Right?
Sorry, was there a difference between GOE and GUE, unitary and orthogonal, or there is no difference?
Oh, there should be no difference, I guess.
No difference. Okay, yeah.
So it's exponentially hard to implement such steps.
But Michał, you would agree that basically the Hamiltonian is dense in some Pauli basis, yeah? That's the equation. Yeah.
Well, in any basis, basically.
Yeah. So that's also something that I also like to discuss. That was a problem for the first paper that was in 2002, where I was focusing on diagonalization. So initially I was studying the Wegener-Guazek-Wilson flows, which are defined for the Hamiltonian. Today I was talking about a flow that is defined for the state and it cools down the state. There's also a double bracket flow. Let me show you here. Note here. There's a double bracket flow that we can define, which will be diagonalizing for you the full Hamiltonian. And when people were asking me how fast does it run, it's very tricky because in principle, I find the full diagonalizing unitary here, but actually do I want to find the full unitary? And the answer is no, for the same reason that Michał said, because in the middle of the spectrum, the eigenstates will be random. And there's basically no structure in such states, and there's no point in approximating such states. So I'm trying to find somewhere, I think I'm showing the spectrum. So in the middle of the plot, we have a typical spectrum for a Ising model, maybe with some longitudinal field. If you ask for eigenstates corresponding to those eigenvalues here, those are more or less random states, and we know that, I mean, there's fairly good theoretical understanding. So actually this is more realistic and this will be quite difficult to do. So that's maybe just to say there exist algorithms of the type that I said for the full diagonalization. And then we were using application of those algorithms from the first paper, and we have actually gate bounds. So this is maybe just one example. It is still okay to be applying those full diagonalization unitaries, trying to get the ground state, because what we found is we can actually compress a bit. So if you start from a VQE, it will get in to a plateau, and then we do just one step of this kind of double bracket iteration. And between 40 and 75 CZ gates per qubit, so it's actually a very shallow circuit. It drops you fully through this barren plateau here, and you drop to the ground state more or less the way you want to. Right now, I'm working on applying this on Quantinuum. So the code here was done in a collaboration with the Kibo team. And we are actually working on running this on Quantinuum. And basically the problem is more how to see, okay, sorry. So we get such a good approximation that the problem is whether you can measure such small values to show that you're dropping down. Because it's noisy, so you have some statistical errors and so on. But the circuits in the appendix, we give a 50 CZ gates per qubit circuit. I mean, this kind of stuff you can run on quantum hardware. So yeah. So basically from the paper for the full diagonalization, we studied the circuit depths, and this is looking quite nice. But in this paper where we got the nice circuit depths, it's kind of a heuristic why we go down. I mean, you can argue a few things heuristically, but then we have the paper that I spoke about today, where we do the double bracket quantum algorithms for imaginary time. And that's more or less a summary of that's all the papers we have so far.
So I propose that because we sort of exceeded the time quite significantly, that we maybe close